If you would like to follow along with the notes, exclamation mark notes if you're following on the chat here. If you're watching on YouTube, the link for the Google Drive where you can find all of the notes for all of the discussion series is down in the description below. All right, so we are on quantum computing part 11. Where did we leave off last time? I don't have like a good last time song transition. Last time. No, that's stealing. Okay. Last time we discussed Hilbert space. So we learned all about the Hilbert space. Not all about, but we learned enough about the Hilbert space to learn about, why we use it so much in physics, and when we talk about it, what do we actually mean by it, and in physics, quantum mechanics more generally, but the garage mechanics. The garage mechanics is what I said. I don't know what you heard, but we did a discussion series on the garage mechanics. So the Hilbert space is just the space of the. It's an inner product space, with a vector space where the vectors are the states that we use to describe, the system. So it has many sorts of forms. It could be infinitely dimensional or just have a very finite amount of dimensions, whatever vector space you're working with for that system. We also went over inner products very thoroughly because, well, we wanted to talk about Hilbert space as an inner product space, and product. Okay, so we talked about the inner products a lot, and then talked about some of the identities, the properties of inner products, what they're used for, and saw some examples of how we use them. We're going to see a few more examples today, I think. Maybe. Don't remember now. But then we finished with... Oh, and then we also took the inner product and went to the... talked about the Cauchy-Schwarz inequality. Now, we studied eigenvalues and eigenvectors, and we found a very interesting form for eigenvectors and values, the equation of this, which is very general, except we kind of made it quantum mechanical by adding a state to it like that. But it's kind of a general thing where we have an operator, we have the eigenvalues of the operator, we have the eigenvectors associated with that operator, and I also drew a lot of analogies to this equation. This very famous equation shows up many different ways as like the Schrodinger and the Klein-Gordon and the Dirac. All of them can sort of be extrapolated in the different notations, because they do change notation, whether working in states or fields or whatnot. But they all kind of extrapolate from this same idea that the operator minus the eigenvalues times the identity, multiplied by the eigenvectors associated with each eigenvalue, is equal to 0. And this has a lot of interesting... have you ever studied materials physics? Yeah, kind of. I do that a bit now, actually. I do that a bit now. Like, I spent the last semester working on advanced condensed matter physics, so we talked all sorts about, different lattice structures and cuprites and carbon structures, graphene, graphite, things like that. I did that type of stuff. So some. But I'm not an expert in it or anything. So we ended with this and where it shows up in quantum mechanics. So, now, let's first start with adjoint. Now, the adjoint is a process we use in quantum mechanics. It looks like this. I know there's a mathematical adjoint or not, but this is specifically, this is specifically used for quantum mechanics. We define it as the transpose of the operator and then complex conjugate that transpose. I don't know what the adjoint means mathematically. And when I say mathematically, I mean to mathematicians, but this is what we use in quantum mechanics. I actually don't even know if they're relatable. I know nothing about it, but I do know that it exists. And let's see here. So we have the adjoint. So an example of this would be like if you have a matrix that looks like A, B, C, D, and then you want to take the adjoint of that matrix. You are going to complex conjugate each term for the complex conjugate part of it, and then take the transpose, which it basically flips the indices. So if you labeled this 0, 1, 0, 1, and this, so this one is 0, 0, this is 1, 1, this is 0, 1, and 1, 0, then you flip the indices, and you get B down here and C up here. But some important properties of the adjoints that might show up. I know this is a lot of technical stuff. We will have a little bit of a hero at the end of the story in some regard. And then this is all stuff kind of building up to when we actually start hitting some quantum computing phenomenons that we know. This does not extend to infinite dimensions. Interesting. Yeah, I don't think operators extend to infinite dimensions, so that's what I was more confused about. But nevertheless, so I guess it couldn't if adjoints don't. So properties are, if we adjoint the product of two operators, then we have to flip them and take the adjoint of each individual operator. Notice when you take the adjoint of a state, we get we just get the complex conjugate of that state. So if you have an operator applied to a state and you adjoint the whole thing, then you just get if you have A applied to a ket, then you'll end up having a adjoint applied to a bra of that same vector. Okay. Tensor products. That's kind of like a big thing for us because notationally, like the states can get a bit, like states are nice and we have good ways of handling states, but if you're like new to this and you want to write everything out in vector notation, as in not bras and kets, and also not like matrix form but like operators, then what? A slinky? Oh, tensor. I see. Got it. But yeah, so a tensor product. Think of a connection. So basically, the idea of a tensor product is you're connecting small vectors, small vector spaces together to create a larger vector space, and that's very useful in quantum mechanics, as we're going to see here in a second. The idea is, so suppose you have V and W. Okay, these are going to be our tensor spaces, or our vector spaces, excuse me, that we're going to be talking about, with V being M dimensional and W being N dimensional. We'll just say D for dimensional. Then the tensor product between V and W, tensor's product denoted with these O times is what we write in LaTeX, or just, a little tiny circle with an X through it. And it's so this has a dimension of n times m. And it's an nm dimensional vector space. Now, the elements of this space are linear combinations of tensored states. So you might think of something like this, where you have a state that you can tensor. So state in V and a state in W will also be tensored together, and you can write like that. Our notation that we're very commonly going to stick with, unless we're writing down properties, because I'm going to write down a bunch of properties, I'm going to use this notation. But a notation that you're kind of used to seeing, and that we'll see a lot of, is just see something like this, VW, right? There's all sorts of very helpful things we use in quantum mechanics where we write a state like that. Think about all of the quantum numbers that are assigned to like particles, right? You could think of those as being tensored states together. Like those are all just how you write it, but we don't ever really teach that in intro to quantum mechanics. You won't learn about that until like your advanced quantum mechanics, or maybe someone might make a mention of it or something like that. But it's not, tensored products are usually not what you're going to see your first time around quantum mechanics. So, but they are very helpful. Again, if you're going to want to do vectors and stuff and matrices, instead of doing states, then if you have a 2-qubit system, you're going to be writing out very large vectors and 4-element vectors and 4x4 matrices and all this other stuff. What if you have a 3-qubit system? Well, it goes up by 2 to the n, for how many qubits you're working with. So now imagine trying to solve a system with, 64 qubits. You have 2 to the 64 long vector and matrices that are 64 by 64. It gets messy. They did come into play. Cool. So you did see them a bit. Yeah, they're not really talked about too much in Townsend. I think they are talked about some, but not a lot. But I learned about, and we did talk a lot about them from Sakurai in grad school for me. Okay, next up, the properties of tensors. Tensor products, excuse me. Okay, so for an arbitrary scalar z, if you multiply through by a tensored state. Now, I'm writing all of these properties down. They're in the notes. And again, we'll just refer back to them every once in a while when we need to. But if you have a scalar multiplied by a tensor product, the scalar can be applied to either of these states. Z times V tensored with W, or V tensored with Z times W. Both of those work fine. As you'll see why when we actually show some examples of these written out for us to see. And then how about for arbitrary V1 and V2 in this vector space of V, we might see something that looks like this, where you have V1 plus the linear combination of V1 and V2 times, tensor product with the state W that happens to be in vector space W. Then this will be this will also be equal to V1 tensored with W plus V2 tensored with W. And then the opposite of that is true as well. What if you have V tensor product with W1 plus W2? Now, this has a very specific thing. It's like we can say these properties, but the reason why I don't just say this 2 and 3 are the same is because order matters for these. As we're going to find out again once we see some examples. Order absolutely matters for tensoring products together. Oops. So that was right. V cross W1 plus V cross W2. So again, we're just now tensoring the products together, or tensoring. So we can tensor V1 to W and V2 to W, but then likely, just like that, except the opposite order, we can do V to W1 plus V to W2. Notice how we can't just easily interchange these back and forth. So those are some properties of tensored products. Now, you could also do, so suppose A and B now are operators that act on V and W respectively. Okay? So now we have a tensored product where we have the tensor product of operator A and operator B. Operator A works on V and not on W, and operator B works on W and not on V. That means that there's, so if we actually take that and multiply it, or apply it to the tensored product of, lost my spot, arbitrary states V and W inside of their vector spaces, then we can simplify this to A applied to the V, tensored with B applied to W. Again, A is, and this happens frequently, like if you, this is most noticeable when you're working in occupation basis, when you want to apply so say you have a series of holes on a chain of electrons, and you have an electron here, and you want to apply a creation annihilation operators. Creation annihilation operators are not going to work on every single one of these states. All of these states are basically being tensored together into one larger state. That's the whole idea of the occupation basis. You have one large tensored state consisting of a bunch of zeros with one particle in one of the spaces. So suppose you want to annihilate it here and create it here. Well, your annihilation vector is going to hit every single one of these, but none of them are going to matter because the only one the annihilation can hit and actually do something to is this one. Or you can be more specific and have subscripts about the annihilation vector and say the annihilation is to annihilate the particle on the second space, and then there's a creation operator that will create a particle on the last space. And there's different ways of applying vectors a different way. Every relativity course, yeah. True, and people ask me that all the time, and I just still don't have a good answer. But anyway, so let's do some examples of tensored products. And you're going to see soon, very soon, why this is helpful when writing down large numbers. Like, there are large quantum computers that exist with 32 bits of information, so that's, I mean, nobody was going to write a vector 32 elements long. So some examples, let's do two examples. Let's do one very simplistic example. Let's tensor two vectors together. So what does it mean when you actually tensor vectors together or states together or operators / matrices together? What does it mean mathematically? Well, you're going to apply, basically it's multiplying all of these elements by both of these elements. So let me write that out, and hopefully this will make more sense. Think of having 1, 1, and 2, 2. And then multiplied by 2 and 3 and 2 and 3. So basically I'm multiplying 1 by 2, 3 by 2, and then 2 by 2 and 3 by 2. And that's how we tensor products together. So now we're creating a 4-dimensional vector, or well, you know what I mean, 4-element long vector. And I'll have the values of 2, 3, 4, and 6. So that's just one simple example of a tensored product. Let's do one that's much more going to be hitting closer to home. How about if we take polymatrices x, which is equal to 0, 1, 1, 0, and y, which is equal to 0 minus I, 0, and we multiply them, or tensor product them together, x tensored with y. I will give you a second to do that. I'm going to grab a drink. I am parched. But again, think along the same lines, where you're going to have each element of the first polymatrix x written out, and then multiplied by the matrix x itself, y. Okay, so presuming you've started, let's do it. Here we have 0 times our y as the first element. Next element will have 1 times y. Next element will be 1 times y. And last element will be 0 times y. So now what I've done is I've written out my x matrix, polymatrix 0, 1, 1, 0. And I'm applying to each individual element a multiplication of the y. So then that looks like this. 0, 0, 0, 0. For the top quadrant, 0, 0, 0. Anything times 0 is going to be 0. Same thing for down here. Now the off diagonals is just being multiplied by 1. So that's going to be 0 minus I, 0. And here will be 0 minus I, and 0, and there we have our tensored product. Notice how I started off by saying tensor products. If one vector space is n and one vector space is m, then the tensored product will be n times n. This is a two-dimensional matrix, two-dimensional matrix, four-dimensional matrix, 4 by 4 matrix, 2 by 2, 2 by 2, 4 by 4, right? So this makes perfect sense. Now, a very helpful notational thing that will, what is that? I did it again. A very helpful notational thing is that we will also have a state psi tensored like this. And basically that is just saying that we're going to take psi and tensor it to itself k amount of times. So that's what we're talking about when we're doing this. We're going to tensor this psi towards itself k amount of times. This is going to be very helpful for us when we're doing bits, because who wants to write out, again, if we have 32, you know, 0, 0, 0, 0, 0, 0, 0, and so all the way up to the end, right? So x, yes. They're not exactly the same. What would it be, though? We could do it really quickly. Hi. How's it going? I am streaming. Hi, honey. I'll be in soon, okay? Kodami, thank you for the follow. Welcome, welcome. Would it be different in this case? Hold on. I actually have to try to figure it out really quickly. The ones matter, but it doesn't always necessarily matter. Oh, yeah, it would be different, because here you'd have minus I, here you'd have I and I. So, yeah, they'd definitely be different. So, yeah, so the order does matter. But this is nice because it makes it so much easier to handle large states of qubits. Last thing I want to talk about is almost last thing I want to talk about is the trace. The trace is very helpful for a lot of things in quantum mechanics. We'll talk a little bit more about it when we get to probability densities. But for now, I'll just tell you what the trace is. The trace is nicely written as the sum of the diagonals, of a matrix. If we talk about the trace of matrix A, mathematically we define it as the sum over all of I for all of the diagonals of I. Notice how this index here is both I and I, so that means A00, A11, A22. So we're just summing down the diagonals of a matrix. There's a lot of properties of traces that are very helpful. One is that they're linear. So the following two are true. Trace of A plus B is equal to the trace of A plus trace of B. Another thing about the linear is the trace of some arbitrary constant times A is equal to the arbitrary constant times the trace of A. That's very helpful as well. Also, it's cyclic. So unlike the tensor product, if you have the trace of AB, this is equal to the trace of BA. And the cyclic thing tells a bunch about it. The trace, yes, the trace is cyclic. So now we have this last thing I want to introduce, which goes with the adjoint. I'm choosing to introduce it now because this is the hero of our story today. The trace actually and the unitarity go nicely together. The cyclic property of the trace can actually show you something about the inner product of states with a matrix, but I'm not going to go into all of that. If it shows up, we'll talk about it, but I won't talk about it too much. But the unitarity itself has kind of an interesting thing. So we talked about adjoints, but a unitarity of operator, like U, multiplied with its own adjoint is equal to I, or 1. I. So, is it I? I don't think it matters. I need to know if it matters. So just for my own clarity. I. Okay, they have I in the book. We're going to go with I. Yeah, because that wouldn't make sense dimensionally if it was just 1. So, that's what I thought. But my notes I have 1, so you're going to want to change that in the notes if you're following along. If you're just getting here and you want my notes, exclamation mark notes, and you'll be able to get a hold of them. Okay, so conservation of probability is something that we can learn from the unitarity of operators. Now that's kind of like a fun thing. So let's talk about the conservation of probability under some transformation U. So we're going to have some transformation U that's going to take some state Y to a new state, Y prime, which is going to equal this unitary transformation times the state of Y. Now, if you want the conservation of probability, let's do the other one as well. So we did the ket. Let's talk about the bra. X being transformed to X prime. And this is just as we learned, we'll have X and U adjoint. Now, the conservation of probability means that the probability of X applied to Y is going to be the same thing as X prime applied to y prime with a unitary operator, which is kind of a big deal, right? Because things that are unitary, preserving this conservation of probability would be a big deal. So let's do that really quickly. Let's do, yeah, so if we were to take the inner product of x prime and y prime, we'll get x, u dagger, u, y, like that. Now we know if our u is unitary, then this is just the identity, and therefore we get x and y. Some famous unitary operators are rotation, the rotational operators. That's a famous unitary. There's lots of them. You can just Google a list of unitary operators. But these unitary operators do, in fact, preserve probability, their conservation of probability, so that we know that unitarity has a very physical meaning behind it already. It turns out unitarity has a lot of physical meaning behind it, and hopefully we'll start to see a lot more in. Hopefully we start to see a lot more of that when we start getting into some of the phenomenon associated with quantum computing. But that's it for today.